Good evening. If you hear me, could you please check in? If I can hear from you, my friend, and Ross. No. Once you guys can hear me, could you please give me a green check so I can make sure that you can hear me? I need to hear from Joe, my friend. Thank you. And this is our lesson number 20. We're going to continue talking about interesting topics with circuits. I know circuits in part are an interesting topic, but tonight, if you guys remember, last week, the week before, we covered series circuits and parallel circuits. Now we're going to combine the two together and make an electrical system. Well, we're going to spend some time spending tonight. I don't know about you, my friend Eric, but what we've done so far is we analyzed DC circuits, what we call them DC circuits. Everything that I covered so far is DC circuits, guys, and that's all we're going to do in the first year. We're not going to AC circuit. Let me just ask you, since I'm AC/DC, how you guys have done AC circuit analysis? Have a great, you guys done it in school, AC circuit. And if you forget, AC deals with Z, the impedance equal R plus J, something like this, plus XL or XC. And have you guys done something like this? How about an X for no? How about an XL and XC and Z is R? How about an X? If you have not done these, if you went to technical college, most likely done it. With the XL and XC, we'll do some of this stuff as you guys go through the apprenticeship later on, not this year. So I don't want to confuse you too much. We are analyzing the same circuit. And by the way, my friend Ross, I saw your email, and I said, guys, do me a favor, guys. When you email me about something related to the class, please emphasize that you are in my Tuesday class. I don't know, I teach a lot of stuff. I teach for ME, I teach the exam prep for the master electrician, the journeyman parliamented. So I teach 16 hours of master electrician exam prep. And I also teach code update. I teach the 2 hours of continuing ed for the electricians and for the masters. And I teach the apprenticeship. I teach for Dunwoody the same thing, guys. So I have a lot of students. I apologize. Russ, my friend, I did not recognize your name. I should, but there's so many names. So if you email me anything related to the class, just emphasize that you're Tuesday class. So that makes it easier for me because I get a lot of emails from a lot of people. So if it's something like what you emailed me, Russ, about the certificate for the continuing ed, I teach this one for many people. So I'm sorry I did not recognize your name from the email. My apology. So what we're going to be doing, guys. So if you email me, please just always indicate your MEA and Tuesday. It seems it's getting tough a little bit. Here tonight, I will go and review as we have done in the past. We will review the quiz. Before I review the quiz, my friends, can I ask you any question about the quiz in particular that we need to go through? I always go through the quiz, but anyone has a question in particular that you would like me to go through? How about an X or no? I will go over them. But if there's anyone in particular you would like me to go over, I will be more than happy to do so. Okay, can I hear from Eric and Dan? Ross, my friend? Yeah. And if you've got anything in particular, unless you're writing me a chat here, just give me an X. Okay. What you guys, I will go back and go over the quiz 19, and then we're going to continue with parallel series circuit combination. For the combination, we'll just go over the quiz and I'll tell you what we're going to be doing. After the quiz, immediately, Brenna, we will be going over parallel series circuit. For series circuit, here's how I do it all the time, guys. I go over resistors in parallel, parallel series, and we go over generators and transformers in parallel series circuit. We talk about how you put them in parallel series circuit. And the system, guys, how do you build an electrical infrastructure with parallel series circuits? Exactly what we do all the time, from the transmission line all the way to the branch circuits. Three theories I would like to touch on tonight, Matthew, my friend. Three theories. These theories are Thevenin and Norton and superposition. These are more more engineering side. I use them when I was in engineering college. They're very powerful. So on them, I don't want to torture you with mathematical analysis, but really handy. So that's what I'm going to do. Before guys, I'm going to go ahead and start the review that as we have done in the past in parallel. So this is just FYI. This is quiz number 19, as we all know. Quiz number 19 in parallel. Number 1, to expedite the process, I'm going to go guys over them. So these are just the rules, and I'm not going to read them. These are all the rules of the parallel circuit. And since well, my friends, we're going to be talking about parallel series circuits, let me quick review it. So the total current adds up in every branch equals the sum of the current through all branches. That will be a view for tonight anyway. Voltage drop across all the branches stays the same, doesn't change. Total resistor is the reciprocal of the sum of the reciprocals. That is confusing, guys, when they say the reciprocal of the sum of the reciprocals. Here's the meaning, and I know probably that why some of you guys got this wrong. When the reciprocal, here's the total resistor, okay? Here's the equal. Here's the reciprocal of all the other, here's R1, that's called reciprocal, plus R2, I'm just going to go to R2, that's the reciprocal. So when they say the reciprocal of all the reciprocals, guys, what they do, then put, and here's 1. See what it means, reciprocal of all the reciprocals. So I don't know if that confuses you. Reciprocal of the sum, here's the sum, that's the sum, okay, here's the mob, of the reciprocals. Here's the reciprocal, here's the reciprocal, and take the reciprocal of them. Makes sense. So this is how you find the R total, aka also, if you guys are, probably a lot of you are familiar with R total equals 1 over R1 plus 1 over R2. That's exactly what we're talking about here. Except to solve for R total, that's exactly how R total means. Okay, any questions about this particular one? How about next one, Chad? If you don't have any question, make sure you're with me and then put your sleep. The reciprocal of the reciprocal of the sum of all the reciprocals. Okay, parallel circuit with applied voltage. Given the applied voltage has a 3 branch with the following resistor, this, and this. Voltage drop across each resistor is what? The voltage drop across each resistor. Number 2, my friend, is D. It doesn't matter, Eric, my friend, if they're all in parallel, the voltage drop stays constant. The voltage drop stays constant. Okay, the circuit has 4 resistors. These all the resistors. 3 of these resistors are branch value, and the 4th is the total resistor. The 4th one, this one, is the total resistor. The total resistance value is, so number 3, our answer for number 3 is A. So a circuit has 4 resistors values listed 1, 2, 3. 3 of these are branch circuits. The 4th is the total. So just to give you an idea, I want to do it one more time. If you guys take the 1 over R total, 1 over R total is given as 60. Just writing it equal 1 over 10 plus 1 over 20 plus 1 over 30. Don't forget that there is the one that's missing. The one that's missing, which is 1 over R4. R4. You guys, if you remember from the days of fractions, I can find common denominator between all these, which happen to be basically 20, 20, 20, 30. So you can find 60 is the common denominator. Is there anything else? Yeah, 60 is the common denominator between all these. So the 10 times 6 becomes, this becomes 6. This is, if you this way, this becomes 3, and this becomes 2, right? Plus 1 over R4. This is one way of doing it. 1 over 60, I'm just doing this one equal, so we have 6 plus 6 equal 6 plus 5 equal 11. 11 over 60, okay, plus R4. Is my math right? Yep. And then move it to the other side. If you get from the days of the friend, move it to the other side. It becomes R60. We have 1 over 60. This is 1 over. Don't this is 1 over. And then you move it to the other side, guys. It becomes 1 over 60. And it's 1 over 11 or 60. And take, why did I end up with a negative number? Okay, blah, blah, blah. Did I do anything? 1 over 60 is the total. It says 3 these values are, the fourth is the total. Yeah, the fourth, 3, the fourth is, I'm sorry. The fourth is the total resistor. I lied to you. The fourth, the total resistor, guys. I made it more complicated than it is. In this case, total equal 1 over this, really. 1 over 10 plus 1 over 20. So parallel circuit has 4 resistor values listed 10, 10, 10. 3 of these are branch values, and the fourth is the total resistor. The total resistance, what the heck? These are values are 3 of these are branch values, and the fourth is the total resistor. The total resistor value is. It is easy as just saying 3. What is the answer for 3 is 8. Oh, I see what you mean. I see some. Juan is your hand is up. Go ahead, Juan.
I wrote to you on that. Just know that the total resistor is going to be the smallest of the numbers.
Thanks so much. You know what? I'm just thinking too much of it. I should have just. You're absolutely right. It's a fourth resistor. You're absolutely right. This is really not doing any calculation. Thank you for bringing it to my attention. This is just, I'm too much into it. I should have looked at it. Bring me all the resistors, guys, and see, pick the one that the total resistor of all. And as you all guys, the total resistor must be the smallest of all. The smallest of all. I'm doing the calculation, chat. Okay, thank you, guys. The smallest resistor, no calculation is needed. The total resistor always in a parallel circuit is the smallest resistor among the group. Good. Resistors has 4 branches. All of them have the same resistance. The total resistor, again, in parallel, if it's 4 guys and all in parallel, the total resistor is their number, that one resistor divided by 4. And as you guys know, this will give me number 4 as C. Shortcut for resistors, if all the resistors are the same, one resistor divided by their number will give you the total resistance. Okay, and to find, circuit has 4 loads, all paired in parallel. Resistor values of loads are these. The total resistor, okay, now this one we need to do the math for now. So trust that you guys do math on this one. You will take 1 over 3 plus 1 over, this is where we need 1 over 4 plus 1 over 5 plus 1 over 6. So 2 ways of doing this. Either you find the common denominator between 3, 4, 5, and 6, 60, 6, and then you flip it, or you use your calculator 1 over plus 1 over plus 1 over plus 1 over, and up, then and if you guys did that 5, your answer should be B. Okay, so that one for what math. Parallel circuit has a total resistor of this amount and the current of this amount. The voltage across the piece of cake, guys. If they give you the amp and you give you the resistor, the voltage is always equal the amp times the resistor. So it doesn't take just to take the 50 times 120. This answer should be directly D. Take 1.2, you times it by 50, that will get you D. Anybody has any questions before we move on? Any questions? Any questions? Moving into number 7, all circuit has total resistor, parallel circuit at total resistor of this amount, and the current is this. The voltage drop on the branch with a resistor of 150 is, if you guys, a parallel circuit has a total resistor, here's my total resistor, and a current that goes through it is this. This is very similar to what we had here. So in a case like this, this is 7, that will be also D. It matters, guys, the voltage drop on the branch with a resistor of this amount. If it's a total, if they're giving me the current, here's what they're saying, guys. The thing is, here's the source here, and the total resistor right here is actually it's a parallel, all of them are parallel circuit, is 50 ohm, and the current that goes through the total resistor is 1.25. If it's a circuit, guys, the total resistor, the voltage across the total resistor is the same as the voltage across every single resistor in your system. Then my answer is 60. Doesn't matter. If you have another resistor right here and a third resistor, when you total them, the voltage across the total resistor is always equal the voltage across each and every one of them. Voltage is constant. 7 has a total resistor of this amount. The ohm is this amount. The current through a branch with a resist. Now the current through the branch, the same thing, guys. Take that one. We have the voltage. Here's my branch, right? My branch is 150. The voltage across that baby is what is the voltage across 50? We need to find the voltage. So here's the if I find the total. So what they want you, here's my total resistor, just show here. If I can take the current 1.25, guys, multiply this one by the 50, which we've done, and then you find the voltage, right? Piece of cake, you find the voltage. From the voltage divided by 150, you current across that branch. A current across that branch. This is number 8. The current across that branch. So the current through this branch, and in this case, number 8. Our answer for this one was an 8. The current was an 8. Because if you take the 60, was it the voltage 50 times? Let me just go through that one. You take the 50 times 1.2 equals 60. Divide this by 150, and you get yourself 0.4. So where did you get the 0.4, guys? You take it from the 60 divided by 150. This is tricky. Any question, guys? Anybody has any question? My friends, about that particular one? Okay, 9. Number is a 900 ohm resistor has a voltage drop of this amount. Consume how much power? This is a piece of cake, guys. They give you the voltage, they give you the resistor. From Ohm law, there's a rule that says if you have the voltage, you square this voltage and you divide it by the resistor. It's a rule that very commonly used. Right? Square voltage, divide it by the resistor, you find the amp. Or if you don't do that, take the voltage, divide by 900, you find the amps, and from the amps, you take the voltage, you multiply it by the amps. So either way, 9H going to be D. Either way, guys, you're going to end up with D. Square the voltage divided by R, or find the current, divide the voltage by the resistor, and the current, multiply the current by the voltage, and off you go. Uses this amount of watts of power as a voltage of this amount, find the current. So, piece of cake, the voltage P equals, guys, as you know, E, the voltage, or V, multiplied by the current. If you give you two things, so here they give you, they give the 0.22, and they give you the voltage, and find the current. I hope that you guys know how to find the current. You swing, I call it the swinging theory. You take this number was at the top, you put it here at the bottom, and you go. I equals 0.22 divided by 15, and if you do the math, that will get you A of an answer. Any question about that? Sticking a little bit longer. with that, U2. Then the following rules for parallel circuit is incorrect. Which one is the word incorrect? So my friend is none of them. B, none are incorrect because they say the sum of the current. They talk about the voltage being constant and the reciprocal. So just B. Number 12. Most are connected in homes. Most of the circuits connected in homes. Number 12, my friend, our answer, of course, is C. All those are connected in parallel, thanks God. Otherwise, you're going to lose a lot of plasma TV. So, power in a circuit as number 13 is if you take the total power in a circuit, it equals the power dissipated, consumed, used, utilized, eaten by every single branch in the circuit. So the power adds each other up. That's easy. Number 14, current flow through each branch of a parallel circuit can be computed if what? 14, our answer is D. We're asking about the current, if the resistance of each resistor and the voltage. So number 1, voltage across resistor, and resistor itself is known. Resistance of each one resistor and resistor through there is no. So in order to find, guys, the current that goes through any branch, like I told you, you have to find at least 2 things. You have to find voltage and the resistor. Oh, 15. Number 15, my friend, is the amount of current flow through a branch of a parallel circuit is inversely proportional to the resistance. That's kind of very interesting, guys. The biggest conductor has the least amount of resistance, and it will take the largest amount of current. That's very common. So inversely proportional to the resistance. You keep increasing the resistance in a branch, and that branch at one time, my friend, that conductor will become an insulator. That conductor will become an insulator. What does that mean? It means the current. If the current this will go down if the resistor goes up. So this is really good concept, especially in the control industry. You keep increasing the resistor to the point where you stop the current from flowing because it just doesn't have ohm. 16. When all the resistors of a branch are of an equal value, the total resistor number 16 is A. As we know, you take one of them and you divide that one by their number. As you all know, now the deal, shortcut for parallel circuit. The total resistor of a parallel circuit is the sum, number 17, my friends, as B here, which is reciprocal of the sum of the reciprocals. Probably that confuses you guys. What is the sum of the reciprocals? An example, what is the sum of the reciprocals? Resistors have values of the following given, connected in parallel. The total resistor of the circuit is, if they're in parallel, my friend, now this is where you're going to go do your math. 240. If I were you guys, if you have a scientific calculator like this, you can do this directly in your calculator as a fraction, or you can use it 1 over 240, 70 plus 1 over 330 plus 1 over 510 plus 1 over 430, scientific calculator. Then equal, they take inverse. What I do is take shift inverse in my calculator, and that will give me the total resistor, which in this case is 18. In this case, 18 is A. Ask you guys any questions? Any question about the quiz? Any question? A parallel circuit contains 4 resistors. The total resistor is given as this amount. 3 of these resistors have these values. Find the. This is what thank you. This is what I was thinking actually when I started coming up with the first example. This one is where I have to take a 120, guys, which is the total. That's what I was thinking. And divide it by 820 plus 1750 plus 1 over 4 0. 4 of them are known, 3 of them are known, the 4th is not, then plus the one that's not known, you call it R R4. I don't know about you guys, but you should be able to solve this problem. How do you solve this problem with a scientific calculator? I will take all these in my scientific calculator, 1 over plus 1 over plus 1 over, then over them, okay? So find answer, and if I'm to do this with my scientific calculator, I start with this one, guys. Take 1 over 20, open brackets, and open the brackets in your scientific calculator if you know how to do that. Then over each one of these numbers plus the other, then inverse the inverse the answer, then hit equal, and off you go. So I hope you guys know how to do that one. Let me just mention a thing. In exam prep with what we teach, they will give you in your journeyman exam, guys, a problem like this. Most of the time they give you only 2 of these. If they give you 2 of these, this becomes very easy. You take the product, remember that product times, this will be 750 over the sum, 820 plus 750, if only 2, and that will be my total. So this one is C, and I know you guys know how to do it on your calculator. If not, you practice a little bit and let me know. We can go over it too as we go through. Any questions about how to do that? Questions? Any questions? I don't want to make it into algebraic mathematics class, but certain things to set up the formula. 3 appliances are connected in parallel. If the circuit to 1 appliance is open, the remaining appliances, thanks God. Answer for this one is A, continue to work in the same manner. Continue to work in the same manner. That's the beauty of the parallel circuit. Okay. Oof. Any guys about the quiz? Any question about the quiz? One more about the quiz. Okay, now moving on, guys, putting all these together, the series circuit. A couple of things, guys, I like to remind. We go into the parallel series circuit. Just very quick review, and I like to put my S for series at the top and my P for parallel, and a few things, guys, how things are related. Let's start. So this is my P and S. Just a quick review for the series circuit. S stands for series, so the right in here is the series, and this P is for parallel. Okay, start with the voltage. The voltage, guys, in the parallel circuit, the voltage V total, this is total, equal V1 plus V2 plus 2. This is the voltage, and equal in a series circuit, guys, equal V1 equal V2. All of them are the same, right? Equal V2. Same, when we write the same. So that you can see how the 2 circuits are side by side put together. The voltage is the same. The voltage adds up in a series circuit. Let's go to the current. The current is the opposite. I total, guys, in a series circuit equal I1 equal I2. As you can see, this is I total equal I1 I2. I want to say the same. Is as if you can see in a parallel circuit equal I1 2, as we all know, I2. So they put together. Let's go directly into the resistor. R total, guys, in a parallel circuit, in a series circuit, equal R1 plus R2. Just quick review for them. R2. This is in a parallel circuit equal 1 over R1 plus 1 over R2. Okay, so that's basically the rules of parallel circuit. The last rule that I like always to emphasize, guys, just which is the power P total, and surprise, P is still the same, guys. So 1 plus P, that's the only rule that stays the same. And this one also equals P1 plus P2. We have the voltage, we have the current, we have the resistor, and we have the power. Question, guys? So that's basically a quick summary of the parallel series circuit put together. Any questions? Questions about the rules before we start analyzing them? Parallel series circuit together. Any questions? In real life, and concentrating, Eric, my friend, only on the power, and Matthew on the power industry. Concentrating on the power industry, all loads and your power sources are going to be connected in parallel. Very interesting. That's the power industry, and I emphasize the word the power industry. We're not talking about electronics now, and we're now talking a lot about control. In the power industry, almost 99% of your loads are going to be connected in parallel, and your generator sources will be connected in parallel. So basically, here's a real application, guys, situation. You have, just to summarize, you have a transformer here, and I'm waiting from this transformer is my panel coming to my panel. Here's 4,000 amp. 4,000 amp. Is my transformer. This is going from the utility. I have my generator, my big gen in here, coming directly into my 2,000 amp. 1,000 amp. This is my switch gear right in here. Okay. And then from here, I went and I put my say 1,000 amp here to feed my chiller. That's a typical application in a commercial building, right? And grab another one here. On this say just 300 amp, and this is feeding a pump. And grab a feeder here, and this will feed another panel, guys. This is my lighting panel. And more interesting, grab a third feeder and come over here to another transformer and feed my receptacle panel. So what you are looking at, guys, is basically what we call it one-line diagram for a power system. Now I'm going to show you guys all the loads that I'm going to analyze are connected in parallel. I'm only showing one line, but all these loads, this load here is connected in parallel, this load is connected in parallel, this load is connected in parallel, this panel is connected in parallel, the transformer is connected in parallel to the equipment. In the power industry, the things that we connect in series are the conductors. Can you guys see the conductors here are connected in series? The overconduction device bringing them in series with the device, and all these conductors, as you can see, to bring the power are connected. These are all in series. Look at the overconduction device. The same thing. The conductors, the overconduction device, conductors, overconduction device. All these are actually in parallel. As you can see, I mean, in series. The green one is cables and overconduction device are connected in series. Everything else is connected, as a matter of fact, in parallel. So that's basically a big picture. I didn't highlight this one intentionally because it's not a load as a load, but I'm not going to open that can of worms. So everything, as you can see, the green for the most part is actually a series circuit. Conductors, and for the most part, the conductors and the overconduction device. So that's really what a parallel circuit is, and in the power industry. So a couple of guys want to go ahead. We'll talk about the combination, how to analyze the parallel circuit, unknown values in the parallel circuit. We're going to touch on a few. We're going to talk a few rules, guys. I want you to understand the most important rule, at least, is the Kirchhoff laws. Kirchhoff laws, guys, you know them. I know you know them when I say them. These two theories, Thevenin and Norton theorem, as engineers to analyze the grid. So you take the power plant in Becker and all the power plants across the U.S., all the cities in the U.S., all tied together in grid. How do you utilize this grid? So if you raise the voltage in Texas, to make sure that to raise the voltage that amount in Texas, so you can make sure it's going to reach Minneapolis at 120. These are what Thevenin and Norton analysis are powerful for. If you heard of them, probably because it's some level analysis, I guess. But these are very powerful. They use them in software, guys, to analyze. Pump the voltage in a power plant in Becker this amount, so it can reach my house in Bloomington at the 120, or plus or minus 3% to 5%. That's for you guys to analyze federal circuit, the combination real circuit is superposition. Superposition is very interesting concept, Joe, my friend. It says, oh, by the way, if you have two sources of power, you have a nuclear plant in Becker and you have a nuclear plant or coal plant in St. Paul. These two plants are tied together. So here's a power plant here, and here's another power plant here, and both of these plants are online, tied to the grid, to the national grid, right? And from here, here's the whole city of Minneapolis, right in here as a load. And oh, by the way, this is the city of Bloomington too. That's how looking at the big picture. And one of these is a power plant, and here's a power plant too. Now, long story short, superposition. This is how powerful superposition is. I will tell you to find the current that goes through this grid. First, consider the first power plant by itself and do analysis. Then consider the second power, do the analysis, and then add them together or subtract them depending upon if they're pushing in the power industry. We add them. Then add them up together. That's what superposition, taking one power source at a time. So these are especially Thevenin, Norton, and superposition. These three guys are very powerful concepts. We will just touch on. Question, guys. How about the next switch ad? Matthew, my friend, are you with me? I don't see exclamation mark, guys, next to your name because you don't get credit. I get yelled at me at MEM. So that's what we're going to be doing. So let's go ahead and start looking at a real life application. A real application, just let's assume this is your one. Let's just make it simple. This is my 120. I know it's DC. I'm going to make it AC. And suppose I have my 20 amp circuit breaker coming to your house, and suppose this one is this resistor here is my wire, the wire resistor, right? And this is my microwave right in here, and also in parallel my dishwasher, and so what did I do? I brought the power right here through a conductor. Conductors are going through the conductors. The impedance of the conductor out of the conductors, from the other side directly to the load. That's what the typical circuit is. And in between, my friends, oh yeah, by the way, in between here's my power source, the panel, and where's the load? I need the load, and my load number 1, and here's my load number 2. Parallel series circuit in the power industry is you have a resistor of the wire and resistor of the load. So when you guys start working on voltage job, you're going to find that if the microwave resistor, I'm just going to throw that. Say the microwave resistor was 100 ohm, the microwave and the dishwasher resistor impedance, let's say that was 50 ohm. Just to give things in perspective, the resistor of the wire going to them is going to be 0.01 ohm. Can you get how small the wire resistor is? So the drop across the wire would be very, 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 very small. For all practical reasons, Eric, my friend, you can consider the R1. You can consider R10. Okay, so that's basically what a real application of power source circuit, in our industry. Yeah. And you guys about this, the load, the source, 5 wires, the impedance of the load is much higher than the impedance of the impedance of the circuit. This is combine the two together. So here's an example, guys. That's what we're going to be doing. When we have a circuit like this, with a circuit, we are combining circuits together, guys, to analyze, to find the total circuit. So I'm going to go after I go over the series parallel circuit very quick, and actually walk you guys through a couple of examples from Delmar, and you're bearing with me. We're going to analyze these parallel series circuits. We're going to do parallel circuit analysis. Okay, series circuit, just a point. Current is the same, resistor is summed up, and the voltage adds up. So this is the most important thing about series circuit. We review it, make sure you understand it. Parallel circuit, voltage stays the same in every branch. The current adds up in every branch to the current, and total resistor is sum of the reciprocals of all the other resistors, as we all know. So these are very interesting concepts about the parallel series circuit before we go and start. Now you have a circuit that you need to analyze. When you have a circuit you need to analyze, you have to combine the circuits together. The most important thing when you have a parallel series circuit, you have to convert them, basically combine the series together, and series and the parallel make a series or another parallel, combine them together. So you keep combining these circuits together until you get what you're looking for. So simplifying the circuit. This is where a lot of people get lost. The good news, my friend, the good news is in your journeyman exam, they don't get you complicated parallel series circuit. Here's a good example where they can get you, and they will take a circuit like this. Okay, and here's, see, that's probably typical of journeyman exam, to give you an idea why you should know that one. Say, suppose this is a 240 power source, AC 240, okay, and I'm telling you that the voltage across this, a 40 volt across this will be given, okay, and resistor here is 100. Here is 50. Okay, and guess what I'm going to be asking you guys? I'm going to be asking you, could you please go find me the current right here, I1 here? Could you please go find me the current in I1 here, I2? If you look at this circuit for a second, I can see a lot of you are going to be panicking. This is what you know. You have a 240 source, a resistor. Let's just say this is R1. I don't care about the value of R1. And I need to find current across the 50 ohm and the 50 ohm and the 100 ohm. And where to start in a circuit like this? Very simple. Well, they're doing this, Eric, my friend. You can combine the two together. You combine the 50 and 100. You don't know what the R1 is. No idea what R1 is. Anybody has an idea where to start in a circuit like this? Anybody where to start? For you guys, you're going to see how it's so easy, it's so simple when you look at it. I want you to think for a second. Think parallel series circuit. What are the rules for the voltage in a series circuit? For the voltage in a series circuit, everybody knows that it adds up. Suppose I want to look at this circuit from here to here. Okay. Suppose I find the voltage right at this point. And if you tell me what is the voltage right at this point, guys, ignore the two parallel circuits right at this point. Anybody an idea to chat with me? You can know what's the voltage right at this point. Anybody can talk? Series circuit, just give you a hint. The voltage in a series circuit adds up. I have 240 40 and another voltage. What would voltage be to add up to 240? That again, what would that add up to 240? 240 and a voltage. What would that be? Can you chat with me? Nobody there? Okay, a good answer. Let me another answer. We got one answer. What voltage right here? I need the voltage right in here. What's the voltage right here? Look at it. Anybody? What's the voltage right here? So that's Matthew, my friend, in your journeyman exam. Well, look how simple that is. The voltage here, guys, equal. If you take the 40 and you do this voltage, they must. So if you take the 240 in a circuit, E equal 40 V, that voltage. Do you agree with that? And if you do your math, then that V that we're looking for equals 240 minus V, and then 200. How simple that is? 200 volts. 200 volts. Everybody know why 200 volts, guys? Because they must, this circuit from here all the way back in up to this point, in all this stuff, guys, all this chunk of stuff right in here, you just put all this chunk in one box, it becomes a series circuit. Can you guys see that? So voltage equal 200. Then I know you, my friend, then the voltage across each one of these is 200, right? If voltage across both of them is 200 and they're in parallel, the voltage across each one of them is 200, right? Everybody knows that? Then if I want to find the current on, okay, Chad, you take the 200, simple that is, divide by 100, and you 2 amps. See how it is? And find I2. I2 equal the same 200 divided this time and double the current. That's 4 amps. Okay, can you guys see that? Everybody can see current I1 is 200 and I2 is 200. Now if I ask you to find I total here, I total equal I1. Remember, guys, what the series parallel circuit? I1 plus I2 and a piece of cake, 2 plus 4. That's 6 amps. 6 amps. Anybody has any questions? This is getting you don't have to do a whole lot of work. All you have to do is understand the rules of a parallel circuit and the rules of a series circuit. Really, when you beginning of the circuit is series and the end of the circuit is parallel. So for practical reasons, guys, I could call this box here a magic box, right here. All these two together, the rule with the R1, they are in series. So the voltage, here's the V plus the 40, they have to equal to 240, or you invented new science. One, it's in series. Can you see that blue stuff that I drew? That's in series. Yes, there are 2 resistors inside it, but they are in series with the R1. That's very simple to get in the exam, the journeyman exam. It doesn't take much, shouldn't take much from all of you guys. If you understand the series parallel circuit, can you guys see the guy analyzing it? And look at the math, how simple the math is, Joanne. Very simple. 200 divided, and that's what they do. 200 divided by 100, 2 amps. 200 by 54 amps, add the 2 amps, 6 amps, done. You don't need a math calculation to change the series parallel circuit rules. Any question, guys? How about to make sure that we did not lose you? So, this example is a good one. You get ready for your journeyman exam. Okay, now we're going to do a couple of combining, guys, simplifying. We're going to do that and reducing and all this good stuff. I have a couple of examples I want to walk you guys through. But before we do that, and this is basically how to combine them and take so simplify, trace the current path. This is just a couple of how to analyze parallel circuits, parallel series circuits, trace the current path, reduce to a simpler circuit, determine the total resistor of the circuit. Though you don't have to do that. Sometimes just you have to analyze it like I did here. Look at that. You just have to look at it and analyze it. Draw the circuit, determine the total resistor, determine the total current, determine the voltage across each resistor, determine the current flow through each resistor. That's the full spiel analysis. That will take you, for when you have circuits with 3 resistors like this, that will take you at least 10-15 minutes to do that. That's if you know what you're doing. But a hint like this should take you no more than 2-3 minutes, just if you analyze it. Okay, then a complex combination, reduce the first. You have a complex with the first parallel block. Look at that. Start with the first, reduce them to one resistor. Combine resistors in series. Combine resistors in parallel. Reduce a resistor block to a single resistor. Combine the first steps. You will do as we go, guys. It makes more sense. Combine the set of second resistors in series. Combine the resistors in parallel. Determine the total resistor. You find the total current and voltage, and from there you transfer this info able to find the current, and all this good stuff that you need. And we're going to be looking at examples, guys, from Delmar book. Before we do that, as we're going to take a class which you know, guys. These are the parallel and the series for the voltage and the current. And these two are more complex kind of deal. I'll leave them until the end, and we'll do a couple of examples. Hopefully, I'm sure we'll have time. We'll do a couple of examples about Thevenin theorem, Norton theorem, and superposition. Before guys, this is Mr. Kirchhoff's. For practical reasons, Brenna, it could have been it could have been Locke voltage line instead of Kirchhoff's law, as the gentleman invented it. So that's why his name is on it. Okay, what does it say, guys? The algebraic sum of the voltage sources and voltage drops in a closed circuit equals 0. This is in a different format. This is just telling you the V total equals V1 plus V2. Nothing other than that. In math format, if you add all the voltages together, it should equal 0. So if I take the V total and add it to V1 plus V2, 0. And you know why they equals 0? I don't know if you know, because this will be negative and this will be negative. So basically you add two negative numbers to a positive number and up to 0 because they're pointing in the wrong direction. So that's that. But I want you to remember that one. V total equals V1 plus V2. So that's what Kirchhoff's law. Again, this is for the series circuit, guys. Now, law Mr. Kirchhoff's is for the current. And again, this is for the parallel circuit. And from here, it says I total 1 I2. Or in Kirchhoff's language, I total plus I1 plus I2 equals 0. Why does it equal 0? And I'm going to use this a different color because this is minus and this is minus negative. So if you add two negative numbers equal to a positive number, well, guess what you have? Say, so this current was 5 and this current was 3 and total current was 8. So reality 8 minus 3 minus 5 equals 0. I don't know about you guys. But suppose same thing for the voltage. Suppose this was minus 40 and this 20. And voltage is 240. Piece of cake, you take the 240 minus 40 minus 200. It should be 200. So not 20, 200. And guess what? That will get you a big fat 0. Kirchhoff's law talks about the current and the voltage for the parallel and circuit. Current equals 0, adding the voltage in a series circuit altogether equals 0. Any question about these two? No, you know them because that's what we use, you and my friends and Matthew. And then that's exactly what we use. Series parallel circuit. Let me give you, it's 55 guys. Let me give you a quick break, and then when we come back, we will and start going over these examples. Just a refresh your mind. It's let's say 702. Let's give you a few minutes, guys. 702 here, and then we'll do the examples when we get back. You can check in, please. Thank you, my friends. Go ahead. Okay, so let's go ahead, guys, and look at a couple of examples in our book. The one to look at, guys, if you do me a favor, ignore this one here. We're going to look at this example first. Number 1. Example number 1, guys, which is A1. Example number 1. So to do this, Joanne, my friend, everybody else, I'm going to go share my desktop with you. So this stuff, as we've in the past, chapter 2, and let's go to monitor 2. Okay, and to do that, to help me, my friends, I want to go. This is where I put you in this so I can hear you, see your chats, and go to. Okay, there you go. Switch these. Takes me a second here to put you guys over here so I can see your chat. What else do I need? This one, feedback. Yeah, I need the feedback. Okay. Okay, let's go ahead, guys, and just look at this circuit. It's a typical parallel series circuit, as you can see. I need the outcome. You can see how the current is coming and goes through each and every branch. Now, the goal is to find the power, the voltage, and the current in every single branch. And then, my friend Eric, has always been our goal, is to find the current, the voltage in each and every branch of these. So what we can do, let me just move this one here. The first thing you need to do, what I always do, is if you guys look at R2, if you look at R2 here, and R3, and these two are in parallel, so we're going to combine them. We're going to combine the two together. So we're going to find an R, and a few of them, this R that says R23. This is a combination of R2 and R3, and this becomes a piece of cake. If you take the 500, multiplied by 750, by the 500, the 750. That's cake, and if you do math on that one, it should end up with 300. Okay, the thing is, you do it. Now I'm going to go R5 and R6. Combine these two together. R5, 6. This is a combination of 5 and 6. If you take chat, 600, multiply the 600 by 900. Okay, and divide the sum. Now, froze in analyzing the circuits, right? Plus 900. And if you do math, this baby, 100 should give you 360. That should give you a 360. Okay. Now, in reality, I've just eliminated this box, guys, here, and I created one resistor instead of two. Can you guys see what I'm doing here? This box has been eliminated, and we created one resistor, and this resistor is equal 360, and this resistor here equals 300. So basically, the two resistors together. Any question about this? Any question about combining it? Any questions for your feedback? Just make sure that you're with me. Any questions? Any, my friends? I hear, so I can. My friend Gerald is the only one who puts the video here. I've got your side. What's going on with the rest of you guys? Where's your video here? Turn off. Gerald. Let's see, Joanne's here too. Oh, there's a few of you guys here. Okay, so let's look at this. I found the combination of 2 and 3, 3, 5, and 6. Now, you're not going to see this on an exam, like general exam or any of these exams. You're going to see on Chad's exam, but on any other exam. Okay, so we combine the two together, and if I continue doing what I've just done, your circuit is going to look like something like that. That's what the combination that we've just found 300. Can you guys see the 300? So when you combine them, joining them, I don't know if you saw how we did that. This is the new that I found. Okay, the circuit have just turned into a series circuit, and what you guys analyzing a series circuit is a piece of cake, because now I can come and add these resistors and find the total resistor. Add these resistors and find the total resistor. Okay. So what does the total resistor mean? Meaning I can get rid of all of them, and I find then the total resistor that can replace all of them is basically the sum of all these resistors. And found it when you add it, 1200. This is at 1200 ohm. So this means, my friends, what this means, it means, Joe, that you can add all these resistors, get rid of all of them, and replace them with one standalone resistor that's 1200. Where did they come up with the 1200? The 1200 is, you take this, you add it to 300 plus the 400 plus the 360 plus the 260. That should add up to 400. Okay, now why did they do this? Because I need to find the I total. I can't find I total, and with B total is 120, guys. So I don't know about you, but I total, I find two things about one branch, I can find everything else. So 120 divided by 1200. So if you divide one, you got yourself the voltage, which is in this is 0.1. In this case, it's 0.1. 120 divided by okay, which is 0.1. So the current, my friends, is actually 0.1 amp. The current going here is 0.1 amp. Now I found the current, which is 0.1 amp. Can you guys see that? 1.1 amp. Let's do a total resistor. We found the total resistor is at 1200 ohm. I go to my circuit. I don't know about you guys, but it doesn't take a genius to discover that all the currents now, let me change the color here to red, all currents now all of a sudden become 0.1, the current here is 0.1, the current here is 0.1, the current here is 0.1, and the current here is 0.1. And if I have the current, let me just do it for this resistor. If the current and the voltage, then voltage here becomes 0.1 times 250. Supposed to be times 1 times 250, and that will give you a voltage of 25, right? And if you do the same thing for each one of them, guys, you will find you do the same thing for each one of them. You're going to find that the voltage here is 36, and the voltage here is 144. Voltage here is 30, and voltage right in here is 50. Okay, format, let me just do it for the 30. You take 300 and you multiply it by 0.1. And then you guys, if you do that, that will get you 300. Any question guess how we came up with these voltages? Any question how we came up with these voltages? Find the total current, find the total current, and then the total current you multiply by the resistor or the combined resistors, find the voltages across each one of them. Any question, guys? Can I have a feedback from the rest of you? Okay. So I don't know about you, my friends, but the resistor number 7 is completely, now I found everything I need about it. Resistor number 1, I found everything I need about it. Resistor number 4, I found everything I need about it. Can you guys see that? These resistors are, I found everything I need about it. I find the power, I find the voltage, the current, and the resistor itself. Now I want to bring to your attention that one thing is still missing. I need to go back and expand this branch and also expand this branch so I can find the current in each one of these, the other resistors, right? So that's the 2 and 3 and 5 and 6. Remind you guys, the voltage 30 volts is across both of them. And 36 is across both of them. With this view, guys, any question how we found the current? We multiply the current by the each resistor at a time. We found the voltage across each resistor. And oh, by the way, my friend Gerald, if you add all these voltages, 15 plus 30 plus 14 plus 36 plus 25, I hope they equal 120. Okay, I see your hand is up. Unmute you. Go ahead.
Well, I'm still confused on how you combined it, 3 and 5 and 6. How did you combine those?
Okay, let's back one step here. Okay, here, are you okay up to this point here?
Well, okay, once we get it into the series, I'm not sure how we combined those two resistors.
Yeah. Can you see my view right now? Okay,
yeah.
I'm going to start right here. Let's go combine them. I'll go put myself in a pencil here. Okay, now you see this is the resistor here, and this resistor here are in parallel, right?
Right.
In reality, they look something like this. Right. This is my this is 500. And this is 750. Okay. Okay. Does it sense right now at this point?
Yeah.
Okay. Now they're in parallel. You agree with me that they're in parallel? They look in parallel. Now I'm going to combine them in one. I'm going to combine in one. That red one. How am I going to combine? There are two ways of combining them. Either you take 1 over R total equal 1 over 500 1 over 750. That way, that's a long way. The other way is to take the R total. There's a rule that says the product over the sum. So you multiply them by each other. With only 2 at a time. 750 divide 100 plus 750. So you see what I'm doing? There's two ways. Either you do it the first 1 over 500 plus 1 over 750, or you can take the product divided by the sum. Does that make up to this point?
Yeah.
And if you do them, this should give you 300 volts, right? 300 ohm, I'm sorry, 300 ohms. So in reality, it becomes the 300 ohms. And all this, cross it for now. Does that make sense?
I'm going to do it on the calculator.
Okay, so you have 500 times 750 equal divide by. If you have an scientific calculator, you have to put brackets. I bet you that's what is causing you trouble. 760, close the brackets, equal. Close to 300. You got something similar? 500, 750. You come up with 5 times 750 equal divided by 500 plus
I keep 1500.
Anybody coming with different number, guys? Do you have a calculator? Do you want a scientific calculator? Okay, here's what we're going to do. First multiply, then head, then you know how to open brackets. There are brackets. Let me see if I open brackets in the scientific calculator. Then add them up. Equal. Bracket after you're done. This is the brackets right here. So by each other, 500, 750 equal. Divide. Open bracket. Yep. Plus. Okay, 750. Always the calculator. It's almost always a calculator ratio. Okay, so that's basic. And the same thing we did this one. Do you understand?
Yeah.
So we'll let you mute you here, don't mind. Okay, so we got these guys. We got these, and then moving to the and we combine them. Now remember, we found the amps. We have the amps and the voltages across each one of them. And I said, I need to go expand, and this. Everything else is done. I'm done here. I'm done here. I'm done here, and I'm done here. I just need to go back and expand the two into two resistors. Remember, it used to be two resistors. So what I'm going to exactly do, and close that one, go back. Now, guys, now we expand it. I want to bring to your attention one little thing when we expand it. I want you to look at the voltage here. Maybe this is not the right color to look at. Let's go back here, grab a different color, maybe yellow. Can you see that the voltage here and here is the same? I started with this voltage, the voltage here, and the voltage here is the same. And then, if I voltage across this resistor, I take the 36, color red. I take the 36, guys, and divide the resistor, which is 600, and that came up with 0.6. And the same thing for the bottom one. Take the same 36, because it's simple, voltage is the same, divide 900, 3.04. And token will be said about that, this resistor here. You take the 30, divided by 500, 0.06, and the last one is in 30 because it's in parallel, 750, I get you 0.4. And in up, guys, if you, I don't know if you see, if you add the 0.5, add to the 0.4, I'm sorry, 0.06 to 0.4, that will get you 0.1. Is any question about how we fold? I can't emphasize, this is, as I said, that's where they catch you in the journeyman license, guys. The voltage across the branch is the same, 30-30. Any questions? Okay, as you can see now, we went and we easily analyzed this circuit, my friend. What analyze the circuit, that big fat word means? The circuit means for every component, 1, 2, 3, 4, 5, 6, 7 components plus the source. I found the following. I found the voltage, the current, and the resistor. Oh, by the way, my friend Gerald, if I ask you, can you find me the power across this resistor, across the R4? And you would say, Chad, no problem. I'll take the 36 and multiply directly the voltage by the current that's going through it. So multiply the voltage consumed by it by the current, the voltage across it by the current consumed by it. If you want to find voltage, the power, you take 36 times 0.06. Guess what? You got 2.1 watts across this resistor. Oh, by what the power consumed across that baby here? Let's take 36 multiplied by 0.04 this time. So this is my 36 times 0.04, and then 0.44. So it's a 0.4 and a 4. Any questions about finding the current? Any question about finding the current? Finding the power? Any question about finding the current or the power for this circuit? There's a guess in this particular one. So first as we combine them and we find the total resistor. After we combine them, go ahead and split them in to the current, the voltage for every single component. I call them components or thing component in that particular circuit. Now, that means, Gerald, in a power industry, not a lot. If the impedance of your conductor is 25 ohm, 250, and impedance of your load is 600, you're in big trouble. You're completely big trouble. In the real life, guys, these for power industry, that 150 the resistors, these resistors will be very small, and you never put loads like these in parallel and then in series with other loads. We don't do that. Okay, one more. Any question, guys, before I move to the next example? Any? And the first and the last time you guys are going to hear Chad talk about these, just FYI. After that, we will move into a different topic as you guys move through the apprenticeship. Okay. And guys, how about the next from Jacob, my friend? Where you did I put your sleeve? And my friend and Russ. All right, there you go. Russ, my friend. Thank you. Okay, so look at this ugly looking thing. The new point of view, it could be ugly. If you're making money out of it, it could look beautiful. I have, let's go count, guys. I always like to count how many components. I call them components. Let's count the components. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and the source. I always count the source. Let's say 9, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 components. What does that mean? Meaning I need to find the voltage, the current, the voltage, and power for every single component, except the source. They want you to find that total resistance. This, guys, there is nowhere on earth you can start except by shrinking these together, by shrinking them. Okay, it doesn't take a genius, guys, my friends, to realize that start working from the most inside out. So, looking at this circuit, guys, I want to go shrink these two, take these two together, and I'll do these fast this time. So it will become 270 because they're in series, right? Plus 270 plus 330 plus 330, right? So that will equal to 600 if I do that right. So I combine them directly, no question asked, for 600 ohm. Okay, now I have 600 ohm. Look what I'm going to do, guys. I'm going to go take these two together now. Can you guys see that? These two together. They change our color, so hopefully it makes more sense. Now I have what? I have this resistor and this resistor, and then parallel. Picture. You're going to take a 600 multiplied by 450 because two of them, divided by 600 plus 450, not 250. Okay, and if you guys do this, you put these two together, the 600 and 450, you're going to end up with 257. You're going to end up with a 2, 5, and a 7 ohm. And I'm doing some approximation. So combine three resistors. What I'm going to do, it gets even worse. I'm going to combine. See how I'm combining more now. Look at the second branch. I'm combining more. So I'm going to have how many resistors now? I have the 4. Now I'm including the 300 plus 430. Can you guys see that? Everything that's 4 plus the, or recalculated 257. 2, and that will be 302 plus, that will give me 987. That will give me a 987 ohm. Okay, 7. Now it gets later than that. Now this 987. Look at the last branch I'm going to do, guys. See, I'll keep going. I want to use another branch. Look at this. That includes. Can you get that green one? That's going to include basically. Well, let's do these two together before we do anything else. I can do these two together. That's a piece of cake, Chad. You take the 510 and you go with the 750. 70. Okay. You take 510, you add it to the 750, my friend. And you're going to have, okay, 510 plus 750. I lost my math. 1260. That will get you at 1260. Okay. Now you take all these together. See that? In that box. And I have 1260. 987 multiply 1260, divide 987. It becomes more complex, but really more calculation. 60. Okay, so if you do that, did we get one R 1250, 50? Okay, you find RC, all of them is 553. So this is equal 553. We talk about ugly things. Now let's go back again and use a different color. Now look at my last color, guys. Can you see how I'm going to take all these? Can you guys see that? Now including everything. See that? I don't know if you can see that. Now I have my 543 plus this resistor plus this resistor, all series. I don't know if you guys can see that they're in series. So I have 360 plus 240. We calculated 5553, and guess what? You end up, my friends, with if you love our total. Where's my total here? R could end up 1153 or 115. I'm just do approximation 54 approximation. Okay, so I didn't drive you nuts with all these lines. And what does that mean, Chad? What means is now you have analyzed. I don't know if you guys can see here. I have one resistor, which is my total, across a voltage of 60. So I can total my I total. Remember, I total here equals piece of cake, Chad, 60 divided by 1154. And if you do that, you find 3 point current. The current is going to be 0.052 amp. That's all this, guys, to get to find that the current right in here is actually 0.052 amps. Notice this. I want you guys to look at the same current that we just found. This current right in here, can you guys see that? Would be current that's going through this circuit here. This is through resistor. So the same current is going to be right in here too, right? You guys are with me? And the current is going to split here, and it's going to split back again here. And also, that's as easy. It's going to be the same current in this one. I hope it doesn't so colorful here. Any questions about this? Any question about that? That one. Okay, it starts with these boxes, and I'm using them. Okay, so if I move without driving nuts, move in here. See how we combine these two together? This is basically the 600. Okay, can you guys see that? This one was two of them. Now see, they combine into one. Now I combined again. These two, they keep combining them, guys. Let's just go one more time here. Grab them. Okay, I'm going to combine these two together, and you're going to see how it's going to be combined later on. Okay, combine. Now again, I'm going to combine the 600 with the 450 in parallel. There you go. 600 and 450 equal 257. Now I have three resistors in series. I'm going to combine together. Can you guys see that? The three resistors in series are 987, right? Now two resistors in series, combine them. Now two resistors in series, piece of cake. Now I have another two in parallel. Combine them again, and I go with a 553, 360, and 240. And then, so that's the easiest. Then, as we find, as I said, we add them up, divide the 60 by them, and you get, when you add them up, you divide the 60. This is where you get So as you know, we took the 60 by 1153, and then amps. And amps here, and the same amps here, and the same amps here. Series circuit. From that, we found the voltages here, and we voltage here by multiplying it by the resistor at that point, and the voltage here. And what? Also, we went and we found the power, and we found the power, and found where's my power? I didn't find the power. I don't need power here. And we found the power for these branches, because they're asking us about power for every branch, current, and voltage. Anything else about that? Actions. The only way, when I was a guy in college and I had to do all this good stuff, Byron, my friend, the only thing I got good at it is just by doing them over and over and over. Where would you do it? I guess, other than the example that I gave you guys, the first example is the best example for the journeyman or master. But likely, Joanne, my friend, that you will see something like this on the journeyman exam. Fortunately, I'll take you forever. Okay, that's really time consuming. Move to the next step. Now we found the current, we start expanding. First we contract and find a resistor, then we start expanding again so we can find what's needed to be found. See how we expand them again, guys? Because the voltage stays the same, 28.7. I can find the current in these two branches, but what I need to expand one more. So guys, and look, we found the voltage here, I found the current, and for the voltage before I find the current, and the resistor, I find the voltage. Okay, keep expanding, back again. Now, we expanded this one, guys, and same current, the voltages, expanding, the same voltage, different currents, the current, different voltages, and off you go. That's basically all we need. And you guys notice one little thing, I don't know if when I was saying, when you expand, first thing coming, let me just tell you why it was easy to this one. The voltage is the same here. These is the same. So here, and I can find the current in here, right? And the voltage and the current, I can find the current that's coming into this branch. And if I know the voltage across these two and the current that's going in one direction, I can find the current that's going in the other direction. So that's why from the resistors, you start expanding them, guys, and you find that's going through one branch. You want to find the current that's going through this branch, you just divide the voltage by the two resistors, and then off you go with finding what you want. But what I want to mention before I let this go and move to a different, more interesting, I don't know if more or not, when you analyze a circuit, you are always supposed to bring the following. You're supposed to find the voltage, the current, and the resistor or the power. One of these. You're given two, guys, and you're supposed to find the other two for every single component in the system. In case this is a circuit with 10 components, and we're supposed to find the power, in this case, the voltage and the current for every single component, and exclude the power source. We need to find the total resistor and power and the voltage and the current. Any question about analyzing this circuit? Let's see it. And a master exam. And then there's nothing wrong with it other than a lot of a crunching number. Gerald, my friend, a lot of crunching number. That will teach you how to do crunch number and so forth. Okay, go get off my sharing my desktop. And in reality, Matthew, my friend, the only thing you probably something very similar to that one on the exam. And as all of you want to be a journeyman and masters and power limited and all this good stuff, right? That's my assumption. I hope I mention that all the time. Okay, that's basically what Kirchhoff's law. Moving into any question you guys about the analyzing circuits before we move into a different topic. Any question about analyzing circuits? Analyzing circuits. You to understand, friend, that I have just touched the surface when we talk to Kirchhoff's law, and I want you to understand that if you are to work engineering and so forth, we do analyze circuits. I did not, guys, do a circuit that has multiple power sources. So here, for example, more realistic. Here's the power source here. Plus, minus, come over here, and from here another load, right? Come over here. Here's the power source. Oh, by the way, plus, minus, and here two power sources. That's almost Gerald, my friend. You're talking about grid, a national grid. This is the city of Minneapolis here, and this is the transmission line bringing the power from Becker and the power plant here, transmission bringing it to Minneapolis, and this is another transmission line, and this is power is coming from all the way from Texas. Okay, Minneapolis. That's basically a national grid. You're looking at a national grid. You can add to it, of course. You can add a lot of it's more complicated. And Kirchhoff's law, and I don't want to do it because I really don't want to complicate it, and there is no value for it, honestly, for electricians. As you start adding the voltages for Kirchhoff's law, analyzing them by adding the voltage, starting from this, they call it the mesh. You drop a curve like this. You drop a curve like a current like this. So you analyze the circuits one power source branch at a time, and as you can see in this here, based on what I showed, the current is going to be coming. One is going to be coming from this side. One current is going to be coming from the other side. Anyway, so on this, guys, they come up with Kirchhoff's law, and this is a plus. This is just a plus minus, and moving into and plus minus for this one, and so you can write your voltage as V equal V here, and this is plus minus V2. So E equals V1 plus V2. And so there's a lot of analysis that I really don't want to do it. Current voltage. It's in page 212, guys, for you. So you can see how you can analyze a circuit using a Kirchhoff's law for multiple sources. All right, I will mention this one and explain it a little bit. Thevenin theorem. Mr. Theorem said, oh, the way, the whole national grid that Chad is telling you about, the whole national grid, I can summarize it with two things. And summarize that baby with a resistor that I'm going to name it after my family, Thevenin, and a voltage I'm going to name it also after my family, Thevenin voltage and Thevenin impedance or resistor. So what does that mean? What it means is, for practical reasons, Canada, I can connect Canada here. That black box here that I'm going to connect to A, B, to B could be the country of Canada, and this is the United States of America. So it's USA. Really, I'm not kidding here. That would be the United States of America with all of the national grid summarized as one resistor and voltage connected to what? I'm going to connect the national grid with the Canadian grid or the Mexican grid. That's how powerful this black box is, or so And this black box, guys, it could be at millions and millions, well, not millions, but it would be hundreds and thousands of cities, and power plants and so forth. That's how high in the power industry that Thevenin system could be. So I summarize the natural grid, as I said, with a voltage and voltage source and a resistor, voltage source and a resistor. The examples I'm going to walk you quick through them, guys. About, I think it's really easy to understand. And then we'll talk about Thevenin in a second. So that's basically, well, let's as long as we're talking about, guys, so all what Thevenin did is he said, I can take the whole grid, summarize it in one voltage and one resistor. Okay? So I can connect with national grid. Okay, is how we found it. Computing, we'll get into that one. Now, Norton, my friend, he said, well, I'm not going to listen to you, buddy. I'm going to go summarize my source. With actually a current. Let's go back. I don't think we have. So Thevenin, he said, no, you're wrong, my friend. I'm going to go summarize the whole national grid with current source, okay, and a resistor, and that national grid. I'll summarize it with a current source and a resistor. And you can see that's a current source, not a voltage source, and a resistor, a current and a resistor. So that's basically where Mr. and the same concept, guys. If you look at them, it's completely the same thing. So, and he called R. This is R, called the R Norton after his family, I guess. And I Norton here. I Norton. Okay. So that's basically what this gentleman went and did. And then, I said, oh, by the way, where am I going to connect to our friends, the Canadian now? I'm going to connect at this level. So here's my AB, and here's my B. And where am I going to connect that black box that's going to be coming from Mexico here or somewhere else? I'm going to connect it right in here. So, source of current, source of voltage. A lot of us guys are familiar with source of voltage, but a few of us are familiar with source of current. We can generate it with, well, we can generate with constant voltage, current vary, or you can generate constant current, voltage vary. 95% of what we do in our industry, we generate voltage and the current fluctuates. Sources where the voltage stays constant, but the current stays constant, but the voltage is different. That's all we need to know about current sources used in different industries, from shifting short circuit into a circuit into other applications. So they call it current source, not power source, not voltage source, current source. And then he decided that you can make his circuit. You can make the circuit, guys, a Thevenin circuit. Application, guys, about Thevenin circuit. I'm going to solve this one right in here. So, suppose that you're looking right now here at the circuit, and suppose I want to convert everything that you guys are looking at into a Thevenin circuit. Suppose you want to convert it into a Thevenin circuit. So what you need to do, my friends, is you need to find the total resistor here, and then from the total resistor, you need to find the circuit. Okay, you need to find the total resistors, and from total resistor, you need to find that and we need to find the voltage. Is my source. So let's go ahead and do one of them, and I hate to make an engineering part because they can go over and over again. 15 volts. Okay, so we got our total, and we got 18 volts. Okay, I see what we're going. Okay, so if I want to convert this circuit, and you look at it, a simple circuit is very easy guys to convert it. If I want to convert this circuit into a Thevenin circuit, all what you have to do is go shunt. First of all, go shunt the power source. Okay? It doesn't exist. So, my friend, now you're looking at, and I need to find the total resistor right here. You guys remember that total resistor right here? I'll ask you, it doesn't take a genius, and the voltages out of the picture here. I just put a wire across it. So these, can you see that the 2 and the 6 are in parallel? So then this will create R. So that will be basically in the case like this. It'll do a Thevenin. Don't look at this one. I'm going to do a Thevenin. I'm just going to do a Thevenin. That would be R Thevenin equal. You're going to do an R Thevenin, my friend. R Thevenin would be a 2 6 divided by 2 plus 6. That's a piece of cake, Chad, because these two are in parallel. So this will be 12 divided by 8. 12 divide this by 8. That will give me 1.5. I should know that. You would think 1.5 ohm. Okay, right? 1.5 ohm. It's not just right at the ohm here. 1.5 ohm. Any questions how I found the R Thevenin? Any question about how we found the R Thevenin? All we do is just shunt the circuit. See that, give that 24 volts, and then take the R2 and R1 and find the equivalent parallel circuit. Any question is, so 2 times 6 plus 2 plus 6, that'll give me 1.5. Any question about that? Up to this point, piece of cake, right? No question up to this point. Time is piece of cake. Then, friends, then the voltage right in here. Right in here. This is V Thevenin. V Thevenin. So I find my V Thevenin, my friend. My V Thevenin. I found that one. Okay. If I point my my V Thevenin, then the voltage across this resistor. Anybody knows how to find a voltage across this resistor? How would you find the current, guys? If you take the I coming from here. Let me do a different color now. Let's suppose that we're doing an I is I to here. Well, what's the voltage? The voltage is 24 volts divided by 1.5. We just find this one, right? Let's take 24 divided by 1.5 equal. That'll give you 16. 6. Guys, but if I take the 16 V Thevenin, then Thevenin is actually V across the R4, right? So Thevenin equals 16. Thevenin, the voltage. That's the current. Okay, I need to find the voltage. The current times the voltage times the current. And what was the current that we came up with? So 240 by 1.4. Okay, I'm sorry. This should be, yeah, no, that's 1.5. Yeah, absolutely right. And then on the current, so this is my current. Here's my current, piece of cake, Chad. Then I have 16 times 6. 60 times 6 equal 96. Did I do something wrong? So take the voltage across these. Oh, I did. Yeah, I see. Sorry, we shouldn't have taken, guys, the parallel one. Taking the parallel, that's what doesn't make sense when you do it. Long time since I've done it. Yeah. Let's just take. There you go. You just do the parallel. You don't do the one in parallel. Okay. Let's go a little bit here. Okay. There you go. With this now, if you take the voltage, again, V Thevenin, V Thevenin, and I promise you, you're not going to hear Chad talk about this one again. Take the 24, guys, and divide it by the total resistance, which is 2 plus 2, right? Okay, so it's 24 divided by 2 plus 6 is, that'll give 3 amps, right? 3 amps. That's the 3 amps. And this is actually the current, the current, I total. The Thevenin, guys, piece of cake. You take the 3 and multiply it by R2, which is 6. That gives 18 amps, 18 volts. So you guys go back to your Thevenin circuit now. Look how it looks like, beautiful. Looks something like this. Here's Canada connected to us. It's our Thevenin, which is I found as 1.5 ohm, 18 volts. That's how you analyze a circuit which looks like that. And the Thevenin, and you find the what do you call it? The V Thevenin, R Thevenin and V Thevenin for a circuit. We're going too much, guys, above your head here. Any question, guys, about finding the R Thevenin? R Thevenin was so easy because is there 2 in parallel. Find the Thevenin. Thevenin, guys, is finding the voltage across this resistor. So if you have a voltage of 24 and a resistor of 2 and a resistor of 6, R, let's go erase the whole thing. So, because I think V7 probably confused you guys. So to find Thevenin, to do, guys, is to find the 24 volts right in here and divide it by 2 and 6, which is 2 plus 6. 2 plus 6, and me 3 amps. Okay, that's piece of cake. Then you take, now the V7 is right in here, V7. So what you have to do now, you take the 6, multiply it by the 3, and that's 18. Because the current that came out of here is 3 amps. It's the current that came out of here, the same current here, the same current here, the same current here, came back. So that came up with the 18. How to come up with the 0.5? That's piece of cake. That's grading the resistor and the power source now is gone, and finding the total resistor right in here. And that was 2, that was 6, guys. Piece of cake. So 2 times 6. Was it 2? Let me just see. What was it? 2 6, yeah. 2 times 6. Go back to here, Chad. Yeah. 2 divided by 2. 6. And that we get the what is it? 1.5? 1.5 amps. So that's 5 amps. 1.5 ohm, not amp. 1.5 ohm. Basically, oops, where we found. Let me go back to mine. This is we found the not here. Let me see where my here. Not here. Okay, this is we found the 18, my friends, and 1.5. Here's R7 and R and you're gonna have a chat that you can't believe it. R7. Salt to injury, to add salt to injury. If Mr. Norton, if I want him to be happy, so I have to go find my source of current, guys. Source of current. This is a current source. And what I'm gonna do, I'm gonna put my resistor. Just put myself in a smaller. So by the way, the R7 now R Newton is going to be R. This is the same 1.5. Okay. By the way, what current is that? Look how they do it. They take the 18, guys, and by 1.5. Add 18 divided by 1.5 equals 10 amps. 12 amps. So we have a 12 amp source I connect that 12 amp source in parallel like this. 12 amp source, connect it in parallel like this. And, grab the A from here. Look where I grab the A and the B, guys. This is my A, this is my B. Same thing A, same thing B, and that's where we connect Mexico and Canada across the resistor. So resistor in parallel and a resistor in series. Resistor in parallel and a resistor in series. Let me just actually make looks better if we do it in give me 1 second, gentlemen, lady. So basically here's my source here, current source. So just to make it look like the one before, guys, here. And here's A and B. Just make sure. Here's A, here's my B, and resistor value right in here. And here's my voltage, my current is 12 amps. Question is, any question? You take the whole 18 divided by 1.5. So the whole grid can be summarized into a voltage source of 18 volts and a total resistor of 1.5, or a current source of 12 amps and a total resistor of 1 ohm. Thevenin and Norton. That's basically my show that one. Superposition, guys. The superposition, we're going to go, guys, talk about the superposition in a second. The superposition, as you mean it with one little thing. A superposition, you have a circuit here, a circuit here, a power source here, and a power source here. And this is just a symbol circuit, a power source. So this one, and this is V2. What it is you analyze this circuit. So those that we will analyze this circuit, first we'll drop this source, okay? And current that's going through this circuit, okay? And if you guys redraw the circuit without this source, it's something similar to this, right? Look at this. It's easy for you to analyze, right? Now it comes something similar to this, right? Because the source it's good. So you take the source. So it's a power source. You short. Okay, voltage ESC is a base with a short. Yeah. So remember what happened to this shorted. Then what you do. You opposite. You go here and you keep this, and you short the voltage and find the current again in this circuit coming out of the circuit, and you add these currents. You algebraically. So if some of them is going the opposite direction, you subtract them. So first analyze with voltage number 1. Second, you analyze with voltage number 2. So these two, and then you add them up. Then you add the current that's coming I1 from I1, the current that's coming from I2. Now, my friend, these two currents could be easily negative. This one could be negative. This one could be positive. When you add them with a sign, so they could be, one current could be going this way, and the other current could be the other way. Stop wire. It's called superposition. Superposition. Another circuit, one power source at a time. One power source at a time. Who cares, Jacob, my friend? This is one tool in your toolbox to analyze circuit. So, and I want to emphasize, when you analyze it, you always put the voltage source that you want to get rid of 0. You want to get rid of these 0. This is very interesting. So the current, the second consists of a current voltage is replaced with an open current that the voltage would cause with first. Okay, so that's basically you replace it with a voltage 0. Now polarity observed. If you have a voltage source, you have to replace it by, if you have voltage source 0, if your current source, you replace it by an open circuit. Okay, there are things, Joanne. If I asked you, probably there is some of these stuff, guys, is really engineering part. So I know it's stuff. Maybe the superposition, Norton and Thevenin is as a tough topic. So don't fully understand it. It wouldn't hurt my feelings to tell you the truth. It's still the same thing unless you want to do engineering stuff. Okay, let me give you guys 10 minutes break, and I'll go just walk you quick. Not 10 minutes. I'll give you 5 minutes break. So it's 8. Let's go 8:09. Let's get back at 8:09, and then we'll do a couple of examples, and we'll see what we can do. So don't sweat too hard, Joanne. It really a tough topic. Can you check him, please? Thank you, my friend. Okay, I promise you I'm going to make it as least of a painful as I could so I can move to a different topic. Go just walk you through these theories and how you do the superposition. Just a superposition. So bear with me, I'm going to share my desktop with you and you're going to be there. You bear with me guys for a second and grab these. But before that, I like at least the feedback so I know that you're with me, and put right in here. That will make a little bit of sense. And now I'm going to hear Chad talking about this topic again. Okay, look at this. I have two power lines feeding this Minneapolis through two transmission lines. That's basically what we're looking at. And we need to find the current that's going through this city of Minneapolis, right in here. That's basically it. So the first thing you do is you get rid of this, find the current I1, you see that, and then you get rid of this one, and you find current again into this one, which is called I2. Add them up. You add I1 plus I2. When I say rid of, what does it mean? Get rid of? You shunt them. You put a resistor across them. I used to when I was in college. What does shunt mean? Get rid of it by putting a cable across it. Okay, so that's exactly what we're going to do. So if you guys look ahead, first you shunted it. Everybody see how we shunted them? We got rid of this, guys. So it's one source, and the current is going this way and splitting here and going back, and that's I1. I'm going to tell you guys that this is piece of cake to find I1, right? Because it's one source. You take the parallel; these are in parallel, and you take them this with series. They do. That's source number one. Okay, we put them in parallel. Now so now I found these in parallel, and I find the current. And look at the current is going this way. Can you guys see the current is going this way? Now I do the opposite. So I found based on this with 13 R2, which is based on R2. If you do the math, and I'm not going to do the math just because of the time. If you do the math, you're going to find the I2 and I1 is 0.0023. If you do the math, you're going to find that the current that came from I1 was actually based, if you analyze it, 0.0, this will be a 0.0229. Okay? Move this one, go to the second one now. Now the opposite, so here's the current, we found it. The second, guys, look what they did. They did the second one this time. They should the second one. I want to bring to attention that the current is going to be coming from here. So here's I2, a piece of cake, Chad. If I were you, I will take the 600 multiplied by 300 divided by 600 and then add this one to 1200. That will, if you add them, they'll give me a total resistor. And find the total resistor, guys, you can find the total current. Okay? So anyway, when you add these two together, guys, here's the current. You're going to find the current in in these two. And I go back, then go back again. So back again, go back again, Chad. Then you find the current coming from this circuit. Then find the current coming from this circuit, and what you're going to add I1 plus I2 in this, and it'll give me the I and R2. That's exactly what they're really doing. Nothing more, nothing less. And I'm not going to do the calculation just because. Moving on to now, what happens? We got to get that. Okay, now what happens if I have a current source? Look at this, guys. Now I have a current source. The thing in the current source, guys, you know what they do? They open circuit. Now, same thing. They got rid of it. Get rid of a current source. Get rid of it. On the voltage source, they make it an open circuit. Look, an open circuit. Now, what you guys, but this is a piece of cake analyzing the circuit and for current, and like you can find it so easy. It's 30. Find the current from the voltage source with the 350, right? I just added them up. And if you have your calculator, you take your 30 divided by 350, you get you 0.09. This is 0.09 amps. The first current coming from here, 0.09 amps, all right? Any guys about the first current? How easy it is? The current going through. Any question? 30 divided by 350. Why 350? 100 plus 250 is 350. So the first current. Now let's go to the second current. Look what they do. Then they go short the voltage source. Now the current that's going through two impedances. And if you guys remember how we do that, if you remember with I2, piece of cake, I2 equal 2 FT. So basically, that other resistor divided by the total resistor, which is, I really do that, 250 times 100 divided by 250. I'm sure a lot of you here, plus 100. Okay, so basically 1 times this all times 0.2. Current divider. Do you guys remember the current divider? That's how you find the current divider. So the divider equals the current in R2 equal R1 divided by the total resistor. If you don't believe me, you go to R2. Remember how we said R2 equal I total? That's what I'm doing. Multiplied by R. R basically, that's going to be R1 over R total. Oh, that one, I probably remember it that right. So that, anyway, that one, guys, you're going to find the total resistor. Find the resistor. Current is going to be shared. If there's a current equal, it's going to be sharing it. That's not, okay. No, it's not, Chad. I knew there's something that comes in here. Okay, so the lead. So if you grab that one, my friends, the current that's coming in here, the current I2 is R2 equal 0.2 multiply 250 divide 350, the total. Okay, you take the total. In this case, guys, you take the total and you find the current that's going through here again, and guess what? You add them up. You add the two currents. If sources, then look at this. I have two current sources, guys, and you analyze the first current sources by opening. Look at how we open this circuit, find the current, go back again, open the circuit, find the current, and guess what? You add them up. You add them up. So that's basically, guys, what the circuit is, and analyzing the circuit and so forth. Here, without before losing it, yeah. And guys, I know there's a lot of stuff about Thevenin and circuit, but all you guys to know, really, for practical reasons, being electricians, all we need to know is the parallel and series circuit and how to analyze and use parallel series circuit rules. Thevenin and Norton, even I tell my students it's done with it. It's great, it's good to know, but you're not going to be applying it being an electrician. It's more in the engineering side. Okay, guys, any question about that? You realize it's not, well, rocket science, but it's the value of it for us being electricians is not that big of a deal. Okay, my friends, to stay on track, let me go give you the poll for the night so you can chew a little bit on that before do a couple of exercises here. So let's open this option. Let's go 8 minutes here. Go. If you guys go exercise, do some calculation. Most calculations are based on parallel series circuits. Good news, my friend Eric, is that Thevenin and the Norton is not on our final two. I mean, We really like to touch it. We don't emphasize it too much. Okay, guys, go ahead and start with that one. You guys are really involved, so I'm interested mostly in the Kirchhoff laws, statements, Thevenin, what's the Thevenin, what's in definitions, just the definition. Otherwise, it's involved. Okay. Okay. All good. Here. Okay. I know I completely understand that some of these guys need a lot of more than 8 minutes, so don't sweat it too hard. You should find the figure and um Jesse, my friend, I completely understand it. You need more than 8 minutes to do that, so I completely understand. You do your best on that. But finding him in 4, you should be able to find him, and I don't have the references for version 4. I have for 2 and 3, but you should be able to find him in 4. I still have 1 and find them. Okay, Joe seems well. You can't. I do have my version 4 here, so I haven't checked it. So if you guys found them in before, so don't sweat it too hard. Let me just show number 1 and 2, guys. Straightforward. They should be. This is just analyzing parallel series circuit like we did the 2 identical to the 2 examples. Kirchhoff for voltage and current. I hope you understand it. Current that enters a point. I don't know if that might be confusing, guys. If Kirchhoff say if the current I1 enter a point like this, it's always positive. Leaving a point, guys, is all negative. So this is convention. Entering is positive, leaving is negative. So that's how it adds up to I1 minus I. Oops. This is convention. Say I minus I2, I3 minus I2 minus I3 equals 0. In reality, it's all what you're doing is I1 equal I2 plus I3. That's the same way of writing. If you know algebra, that's exactly the same way of writing. Okay, so that's basically it. There's a couple of Thevenin calculation, guys. At the end, I thought that was really interesting. But calculating, as I said, calculating if you have a resistor like this and another resistor at the power source, and Thevenin, and finding, guys, the total resistor. This would not be. I thought that was really not hard to find. So all what you have to do is just get rid of that and find the total resistor between these 2. So that in this case, that will be your R Thevenin, right? So if you take this is R1 and this is R2, and find a resistor for these 2, just a total in parallel, that will give you R Thevenin. That's a piece of cake. You should be able to do that. Okay, so that's Thevenin. Every one of you guys should be able to do that. The second one is the voltage. The V7 is the voltage right here. V7. So for this one, all what you really have to do is V7 is total voltage, which is this V equals divided by R1 plus 2. Will give actually. Sorry, that will give you that will give you a current first. That will give you current I total, and I total, guys. This is total. Multiply I total by R2. You get a V7. V7 not do. Superposition is a little bit hard. I really understand. Superposition is a little bit hard. So, but it's really for all practical reasons for you guys. Not, really good. Let me just remind you guys, there's really good exercises. I encourage all of you to look at them in the back of the book. Exercise about Thevenin and Norton. If you have a chance to do some of them, the answers are in the back of the book. If you're stuck with something and you want to do it, then just drop me an email. I should be able to walk you through it too. Okay, I will have it at this point, guys, in terms of Thevenin and Norton. Any questions? Any questions? As you say in this class, is just be aware that superposition, Thevenin, Norton are 3 ways, and Kirchhoff's law are 3 ways of analyzing circuits and simplifying it. and find the voltage, power, and current about them, guys. This is the topic. Of the class before, I told you guys about, and I don't know, really mention a few things about parallel series circuits. One thing in the power source that comes to my mind all the time, Brandon, my friend, when it comes to parallel series circuit is power. I'm going to talk about looking at it from a power point of view. From a power view, guys, one thing comes to my mind, as I said all the time, that we do is how we use the parallel series circuit in the industry. I don't know how many of you guys have seen these. This is where you have a string of batteries in a system. So, and I'm going to power these, and these are your batteries, and this is one string number one, okay, and another string. Look what they do. This is to get you voltages in the center. Is by a second string. See, this is putting power batteries in series and in parallel. I don't know if you guys see how they're going to be in parallel in a second here. Okay, and my second string is another one. These are all batteries, all batteries here, and Chad, M. Now I have let's say, guys, each one of these batteries was 12 volts. Let's say 12 volt batteries, and assume that this is that each string has 10 of them. So it's 10 here, and there's 10 here, and there's 10 here. So if you multiply 12 by 10, you get you 120 volt DC, 120 volt DC. Okay. This string, as a matter of fact, right here is give you 120 volts. Then what I would do, guys, is I would go parallel them. They're in series. Then I go parallel them. Look at how to parallel them to get me amps. So I go parallel them, okay, and bring them down here to my, and then I feed here. Here's 120 volt DC. 120 volt DC. That's common practice and data centers. Parallel, they call them a string of batteries. Is string number one, number two, and suppose now why would I do something like this? Because I need more power. Suppose this string is giving me, just for all practical reasons, let's say 10 amps, and it's giving me 10 amps, and this 10 amps. These are in parallel. So what do you guys think the amps here? They're 30 amps. So this is a bank of batteries worth 30 amps by 120. What does it mean, Chad? So here's my 30 amps multiplied by 120, and you know how much power I have in this system to store and utilize. 120 times 30 equals, I have 36 3.6 kW worth of power in this system. 6 kW worth of power in the system. That's a good, and that's one application where you can put the power sources in series together to get you the voltage that you want, which is 120. Then you put them in parallel to get you the amps that you need, or you want, and that you decided to go by, and then the amps that you need. So voltages, guys, more, and also more amps, more power. Question, guys, about this? I thought this is a good application for parallel series circuit of power sources. Questions? That's a place that I know of where power sources can be put in parallel and series, basically to make a power system. Power. I keep emphasizing the word power. Any question about that one? For that, the AC systems, they're all tied in parallel generators with conduits and branch circuits and feeders, all in series in between them. Okay, there's a couple of exercises that I thought, guys, really good. We used to do them in a class before we moved into the online. And if you guys have, we can easily do these. So if you look at the power source, you go adjust these DC power source into the volts. Suppose that just into 30 volts. I bring to attention my friend Joe that this is a voltmeter. It's not doing anything other than measuring the voltmeter. And also this is an amp meter, and it's not doing anything there other than measuring the amp in this branch. Okay, so that's just a few assumptions. Push buttons. I don't know if you guys can see the push buttons here, and a switch right here. So, and there's another switch for each one of these lights. Another for each one of these lights. This is really good exercise where it makes you really understand what the power system is. I'm going to ask you a couple of questions, guys, to see if you understand the power system. So suppose, and listen to me carefully. Suppose that I want to go close a couple of switches here. Suppose I close this. Everything red is closed. I close this, and I close this. Okay? All of them closed. And here's my assumption. All these lights are, let us say all of them are 10 ohms. Each one is 10 ohms. Each one of these lights is 10 ohms. Maybe I should put it this way. Each one of these lights is 10 ohms. They're all equal. Okay? I want somebody to tell me what, okay, did you guys see the assumption? Each one of them is 10 ohms. I want you guys to tell me what would the voltage be across each one of them if they are 10 volts. What would be the voltage across each one of them if they're all the same? Yeah. What would be voltage across each of them? Oh, by the way, this switch is also closed. Can you get that with me? That's kind of idea to understand what's a series circuit. So you guys, and tell me what would be the voltage across each one of them if they're the same, if they're all the same. Each one of them. Each one of them, guys, they're all the same. They're all the same. They're all the same. I see a number. I haven't seen a good number yet. I will remind you guys, they're all the same. They're one voltage. How resistor are they? So, by the way, can you tell guys that I have two resistors in parallel? Two resistors in parallel could be in series and share voltage. What if resistors share a voltage in series, guys? How do they share it? Now, something, right? So resistors share the voltage in series. How do they share it? They share it. Anybody? Equally. They share it equally. So if all these lights are the same, then all of them are, I don't need to know what value is. All of them are the same. Then voltage across one of them, guys, with 15. Why 15, Chad? Because if they're the same, right? They're sharing, look at them, they're sharing a 30 volts, and they're the same. There's two sets of them. One set right here, one set right here. Because in series, because two sets of them in series, now you divide the voltage by 2, and I'll get 15 volts, right? So across each one of these resistors, there will be volts. I don't know if you can see that. Across one of these resistors, 15 volts. Because from here to here, there will be 15 volts, right? And from here to here, there will be 15 volts. Did I close S5? Where is S1, 2, 3, 4? I closed S5. I closed S5. S5 is closed. So switches are closed, and if they're all the same, guys, the voltage across each one of them will be the source voltage because they're sharing the voltage equally. And that's what this is how you kind of understand how the systems work together. Any before I go to my second exercise for you. Okay, now suppose I want somebody to tell me each one of them is 10. Okay, so I have 10. Each one of them is 10 ohm. I have an ohm. I have 10 ohm. I have 10 ohm. I have 10 ohm. Okay, I need you, my friends, and listen carefully. I need you to find me the. I need milliamps right here. Find the current. Each one of them is 9 amps. I want to give you guys a hint. The voltage, if they're all the same, would be the voltage here. We just calculated the voltage, 15 volts. Okay. Okay. If I have 15 volts, the current would be. What would we think? So we know the voltage. Let's just look at the current right here. What would the current be here and the current be here? And what currents do when they come out of this intersection? We'll find the current right here. What would that read? All the switches are closed, by the way. If I mentioned that, all the switches are closed. All of them, the switches are closed. What is the current? Okay. I haven't seen it yet. I've not seen the right number. How do you find the current in each light? Find the current in each light. What would be in each light? In each light, the two currents will add each other's up. So that's basically the key word. The key word is the current here and this branch will to the current right in here. So find the current in each one of these branches. Now we're talking. Find the current in each one of these branches, and if it starts here, all in the same current, right? You should. Somebody else, guys? I see a couple of good numbers. Now we're talking. See that? And basically, you take the 15 volts, divide 10 ohm, that's to 1.5. 15 volts, divide by 10, that will get you another 1.5. Then the parallel circuit rules. And since they are in parallel, they add each other's up as they exit the branches. As they exit their branches, they add each other's up. So it doesn't take a genius to say 1.5 plus 1.5 equal 3 amps. So that's basically how these will help you guys when we do them in the lab. Will help you analyze and understand how the circuit, how it works. And you do the measurement. We did the measurement on this. Okay, so that's the second thing. Now let me tell you one little thing. So this one, I close these. I close these. Okay, I close one. All of them are the same. All the lights are the same. But I went and closed the push button here. What was the voltage across? Would be voltage right in here, and what voltage right in here. You guys, I closed all the switches, including the bush vine. And if this, what would be the voltage? What voltage, guys, across I'm going to V1. I'm going to call this is V2. What would be? All of them are the same size. All of them are the same size. Voltage across V1 and V2. Okay, you guys to look at the push button. What would the push button do if you close it? This will analyze the circuit. Shunt. Okay, I need the voltage V1 equal and V2 equal. I saw one good example example, I see 13, V15, one of them is right, and one actually, both of them are wrong based on what you, the 30 V2 equals 15, no. I look at the push button as pushed in. What happens if you go take a light and tie two wires across the light? What happens if you do that? Well, if you do that in like the real life, Matthew, you're going to short it. But if a series load with it, if there is a series load with it, that's why you don't short. What happens one load? Fixture like this. I'll go and tie wire across it. With the current that's going to go through the wire, and the current that's going to go through there is going to be close to zero. Close to zero. More current is going to go through that across it. Is going to pass it. So the current comes here. Oops. Most of the current is going to go across it. That's what a short circuit is. Very amount of current will go through it. Okay. One more time. Any question about that one? What's the voltage? Okay. Since you guys are stuck, let me tell you that the voltage right here will be 0. Why 0? Because we shunted them. We call it shunted. And the voltage across this one will be 30 volts. So if you don't see that, you might have to work on that one. So because we shunted these, and these don't exist anymore. More current will go right through here, and through these two, then go back to the source. And this, any questions about this? Shunting the circuit, very important topic. And you guys, if you close this one and close this one, then the current is going to go only through this branch, as we know, right? Avoid the other branches. Should be second, and this one, it should be second nature to you guys. So moving to a different topic, resistor, guys, the same thing. 100, 1.5, 1K, 3. So these are all the resistors across in 100 ohm. Change the color. So if I ask you to find the total, close this one, and you the amps, find the amps. Find the current here. Current here. So let me just quick size that one for you, my friends. If you take 1,000 multiplied by, you guys remember, by 1.5, well, 1,500, now 1.5. This is just, let me just try if I can get it. 1.5 divided by 1,000 plus 1.5, 1,500. Okay, that will find this one. Then add it to the 300, add it to this, and the total by the voltage, and that will get you the current. And I don't want to do it because it's time consuming, and we're into the end of the class. So basically, that's what a resistor is. It should be every one of you guys should be able to analyze a circuit like this. Really is. If I ask you after you find the current, find the voltage across this. All say no problem, Chad. It's equal the voltage times the current that you already found. If I ask you guys to find the voltage across this one, be 300 times current I. Okay. And you want to find the voltage across these ones. That's also the same. The voltage, guys. You're going to find that will be the case like this. We found the current. We found these. You're going to be able to find the voltage across them because it's a total. And from here, you're able to find the voltage across these two. Because you find it here, add it to here, subtract the total from 30, tell you the voltage across this one. So that's basically, there's one more thing I want to Okay, so there's a couple of more circuits, guys, how to analyze them. Again, we are in the lab. We will watch and we'll play with them. I'll tell you guys, as you put resistors and lights, resistive loads in series, the lights will dim. That's a lot of people, guys. One. Okay, here's a voltage divider. Voltage divider is really interesting concept. If you find the voltage, remember, guys, the voltage across this one, from the voltage across any one of these, you're going to find the current that goes through it, right? Through the resistor. You have total current, multiply the resistor, off you go with the voltage across AB, BC, or ABAD, or AC, any across any one of these, across these. So, in order to find the voltage across R1, just see the V, this is VR1. What we did, you take R1, the total, which is R1 plus R2 plus 3, and you multiply this by the source voltage, which is in this case where you only 10 volt DC, multiply it by 10. So that's across R1. You can find the voltage across R2, you can find the voltage across R3 the same way. You have a voltage divider, or if you don't want to do it this way, you just find the current multiplied by the resistance. And we do it in labs and so forth. This is an interesting control circuit. Control circuits, guys, as you can see, DC. I'm sure how many guys have done control circuits? How many done control circuits? Green check. Magnetic starter, typical simple way of connecting control circuits. Very simple way. The way for this baby to go, my friends, is you grab the voltage AC or DC, because the power source came from here. So here's 120 volt DC, these contactors. And if you have, if you bring to attention, guys, look at the push button, this the stop one, I'm going to go stop number 1, stop number 2, stop number 3. I have 3 stop buttons in series. The reason behind them in series is because you need to be able to stop from any one of them. Okay. The start button, on the other hand, the arrow. Okay, you can see that I can put 1 million. Well, I shouldn't, but I put 100 stop buttons, guys, in parallel with their counterpart. The start button parallel and their counterpart, the start momentarily stop buttons in series. Okay, that's another thing that you have to pay attention to. We go erase all that one. So if you guys look at this one and this one is in series. Now their counterparts are the push button momentarily start. These are in parallel, and both of them are in series with the coil. And in series with, look at that, we put them in series with the normally closed contacts overload. And there's a holding contact that, as you find, it keeps the coil energized. Keep the coil energized. Okay, so how do you extract this power? The power comes in here. All stop, close, keep moving. Now up to this point, nothing will happen. The minute, my friend, you will push this down, use this. Now power jumped in, energize the coil. What is energized? Physically, mechanically push contacts to close. That's the mechanical. So this contact will close. Now the current is go through this path to using the coil, and the coil is energized. Now this is closed, so we're going to continue going through it, and guess what? Now my coil has 120 volts across it. right? The key point is you need this coil. See that coil? I need 20 across that coil. This coil to pick up. So take voltage across this coil. And but when you're done, guess what happens to these? This particular, see the current goes, now open or move my finger off this momentarily push button. Now the current is flowing, guys, now coming from here all the way. Now I don't have the push button, but I have another path, another that goes through it. Now my coil has 120, and guess what the coil does? The coil will take a magnetic contactors, guys, right in here, and take them all the way to phase A, phase B, and phase C, and energize your beautiful 50 horsepower motor, 50 or more or less, 50 or more. Okay, now suppose something happened and you need to stop that baby, and suppose you're so close to push button number 1. Connect this. So suppose I'm going to come in from here. So I open this. So if I'm the guys, then the power is not going to go through. So I lost. Then I won't lose my power completely. I'm going to be losing my power. So immediately you lost your power. This will open. You lost that 240 across this coil. This coil is dead, and off you go. You know, the vehicle interface is open, and you go back to your system being de-energized. Your system being de-energized. So that's very, very interesting. The big connection goes for a magnetic starter. And so I bring to attention, and to these are the only reason why we throw this one is look how the push buttons are connected in series. Can you guys see that? Start, end, start to end, start to end. The start is the end, start, end, start, end, and then you move. Now the other ones, the and are connected in parallel, start to start, end to end. Can you guys see that? What's in parallel is start to start, end to end, all connected in parallel. And also I put across them and in parallel a magnetic starter holding contact. Then the system goes in series with the coil with the overload contact. So the device is in series, this device in series with look what? With contact. All the contacts are in series with the coil. But the coil, for all different reasons, the coil is actually in parallel with the voltage. I hope you can see that. If you now look at all these connections, because they're not taking any load. 9 o'clock. I don't want to take too much of your time. Any question, guys? Any question about this one? I hope you don't get too mad about Norton and Thevenin, guys. Don't worry too much about it. Do your best on it. The most important thing is to be able to understand circuit using Thevenin and Norton. Okay, one more, my friend. Any questions before you guys go? Week we're going to be, before you guys go, we're going to be doing we're going to switch away from the analyzing circuits. We're not going to be talking more about parallel series circuits. If you have any question about Norton and all the stuff, please don't hesitate to email me. I should be able to walk you next week. Everybody wants to go through it with no problem. And we're going to be doing metering next week. So that's for you guys tonight. If you don't have anything, good night, and we'll see you next week.